All right, guys. Hey, back here with you today to talk to you about some more chemistry stuff. This is the Lewis structures part. So we went all through Unit 5. We talked about the different types of chemical bonds, ionic bonding, covalent bonding, and a little bit in the metallic bonding. So here we're going to get into the structures of with Lewis structures, and these are mainly for things that are bonded together covalently. Things that are bonded together ionically has that crystal lattice kind of structure going on. You just have ions and then the opposites subtract because of the ions. So it's a little bit more simple kind of arrangement, I guess you would say. But we'll get into these covalently bonded, these Lewis structures. I think you probably drew them before a little bit, maybe in physical science. So it's maybe not be completely new to you. So we'll get into this, and I'm going to try to kind of punch this into a couple shorter videos as we go here. So let me back up a few slides. Start out with, it's really all about the octet. We've talked about your different elements on the periodic table and how many valence electrons they have. Group 1 has 1 valence electron. Group 2 has 2 valence electrons. If you go over to boron, aluminum, that group 13, they have 3 valence electrons. Carbon, silicon, 4 valence electrons, and so on, all the way till you get to your noble gases in group 18, which have 8 valence electrons. 8 valence electrons is a full octet. Octet, like octagon, 8, right? So they're happy. They have the number of valence electrons they want. They have a completely full outer shell. So their energy is lower, their potential energy is lower, they're stable. That's where they want to be. So any of these other elements, that's where they're trying to get to, either by covalent bonding, sharing electrons to get to that full octet, or, which is what we're going to talk about today, or that ionic stuff where they're transferring electrons. They're either taking on electrons or giving up electrons, so they end up with that full octet. All right? So it's really all about a full octet. Chemical compounds tend to form so that each atom, either through the process of gaining or losing, that would be ionic bonding, or sharing, that would be covalent bonding, ends up with an octet of electrons at its highest energy level. So where we get the octet from is we're filling the s and the p orbitals, which is what it's talking about here. So a completely filled s and p shell. You remember each s orbital holds 2, a p orbital, there's 3 of them, each of them hold 2 for a total of 6. The 2 from the s, the 6 from the p gives you 8 electrons, right? So there are some exceptions to the octet rule. Hydrogen is an exception to the octet rule. Hydrogen just has 1 electron, and if it gets 1 more, it now has 2. It feels like helium, it feels like a noble gas. Its outer shell, that first shell, is completely filled, so it's happy, okay? Helium, obviously, noble gases we really don't want to talk about in terms of bonding because they don't bond with stuff, right? But it would be an exception too. If you go on to back here, lithium only has 3, right? So lithium is a case where it would be ionic bonding, where it would lose an electron and then end up with just having 2 in its outer shell, right? So it's an exception. Beryllium's exception. Boron's exception. And then there's also exceptions where we get down here from this third period here on over here, from these guys down, they can actually break the octet by having more than 8. Okay, so there are some exceptions to the rule, and we'll kind of talk about that when we get there. Don't worry too much about it now, but just know that it's possible to break the octet. But we have some rules to learn about when it doesn't have 8, when it does break the octet. But generally speaking, what we're trying to do is we're trying to build a structure so everybody gets its 8. Okay. The one exception we will consistently deal with is hydrogen. Hydrogen, you give him his 2 and he's completely happy, right? Okay. So starting off with the first thing that y'all, when y'all did this in physical science, y'all spent some time just doing the electron dot notation. Dot notation, all it is just writing the symbol for the element and then putting dots around that element showing how many valence electrons it has, okay? So you can see here, this is, group 1, group 2, and then over here, group 13, 14, 15, 16, 17, 18, and showing how many valence electrons that they have. So you just simply say, okay, pick an element. So say we say, let's pick phosphorus, and we can look and we can see that phosphorus is, oops, here I'll just go to this one. Phosphorus is right here. So in terms of valence electrons, you would say 1, 2, 3, 4, 5 valence electrons, right? Or it might be easier for you to count backwards, knowing that all the way at the end here, this is 8, right? So these guys have 8, and these guys have 7, 6, and then phosphorus here would be at 5. So if I do the dot notation for phosphorus, then I'm just going to go around and put 1, 2, 3, 4, put 1 on each, kind of like the idea of spreading the electrons out as far as possible. And then once they all get 4, if you still need more, phosphorus needs 5, remember, then we would come back and we would double one of them up. I started over here. It doesn't really matter where you start. You can go 1, 2, 3, 4 and double up on this side, or start at the top. That doesn't matter, okay? But we do give each side 1 before we double up and give any side 2 there, just because of the idea of spreading the electrons out, allowing them to be as far away from each other as possible, okay? So if you do any other element, it would be the same thing. If you take magnesium here, it's right here. So if we do the dot notation for magnesium, it's just simply 2 electrons, right? So you do not put them side by side here. This would be wrong, okay? So we don't want to do that. We put 1 of them, it doesn't matter what side. So if you go 1 here, then the next one would be in another spot, on another side. You have 4 sides to the symbol or whatever. So magnesium has 2, phosphorus has 5, and you can just do any element like that, right? So you pick the element, look, see where it is, what group it's in. That should tell you how many valence electrons it has, and then you just put your dots around it, showing the number of valence electrons. Okay. Let's get back here where I want to be. There we go. All right. So Lewis structures. The basic idea of Lewis structures is we're taking this idea of the dot thing and we're kind of putting them together and showing the kind of sharing of the electrons. And this kind of shows that just a little bit. So you'll see in just a second here. All right, so the formulas, which the atomic symbol represent the nuclei and the inner electrons, the dot pairs and dashes and such between the atomic symbols represent the electron pairs in the covalent bonds. So what they're saying is the symbol itself represents the atom, its nucleus, and all of its inner shell electrons. And then the dots and the dashes, these dots and these dashes here, that represents the electrons that are in that outer shell. The dashes would be the ones that would be bonded together. That would be that would be involved in the covalent bonds. Okay, so anytime you have dots here, like hydrogen is just bringing 1 valence electron. Oxygen has 6, so 2 here. Oops. 2 here, 2 here, and then 2 more here. So these 2 hydrogens, one from the hydrogen and one from the oxygen, they would share with each other. So the hydrogen gets the 2 that it wants. That's forming a bond, right? But also there would be another hydrogen that would do the same thing down here. And then this hydrogen also gets the 2 that it wants. I'm not touching the board, I'm just getting too close to it. And at the same time, the oxygen gets the total of 8 that it wants. So you got 2, 4, 6, 8. A line, a single line, represents a single bond. A bond is a pair of electrons that are being shared. Okay? So obviously, this would be a 1 shared pair, a single bond. This would be another shared pair, and then we have 2 unshared. Oh, sweet Jesus. 2 unshared, and then 2 more unshared. So the oxygen has the 8 that it wants, it has that full octet, and each of the hydrogens have the 2 that they want to get them to feel like a noble gas, helium, right? And then these are just more examples of the same thing, blah, 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 that kind of stuff. All right? Here's the steps that is going to guide you in doing your Lewis structures and setting up your Lewis structures. So I'm giving you these steps. I think they're pretty clear, and just go step by step by step, and you would end up with a correct Lewis structure at the end. Okay, it may take a little bit of practice. You may have to watch the video a couple times. I'm going to share like several little practice videos of us doing examples, and I'll actually share some other videos where other people have done examples for you. So if you struggle with it just to begin with, it's okay. Okay, just continue watching and continue paying attention, and I think you'll get it at the end. It'll be fairly simple. So I'm just going to read through these examples real quick. I'll do like one example with you, and then I'll have other example videos that are separate, so the video doesn't get too long. Okay, so just the simple steps for Lewis structures. Number 1, the first thing we want to do is we want to determine the type and the number of atoms in the molecule. Okay, what type of atoms are we dealing with? How many of each of those atoms are we dealing with that's in that structure, that's in that molecule, that's bonded together? Okay. Second thing we want to do is we want to determine the total number of valence electrons available and the atoms to be combined. So how many valence electrons in total am I working with? So when we put the structure together, I'll just go ahead and put on the board here. This is the first example here. CH3I. So we can see here, step 1, how many? We have 1 carbon, we have 3 hydrogens, and we have 1 iodine. That's determining the type and the number of atoms in the molecule. So this is the molecule. I've got 1 of these, I've got 3 of these, and I have 1 of these, right? Well, the second thing is to figure out, okay, how many valence electrons do I have? Okay, so what's the number of valence electrons I'm working with? So how many valence electrons does this guy give me? How many valence electrons does each of these give me? How many valence electrons does this guy give me? And then I can add that up to figure out the total number of valence electrons I'm working with, right? Because I can't just create more electrons or just magically lose electrons. I have to work with that number of electrons in order to make everybody happy. So everybody gets what they want, because if they didn't get what they want, then the bond wouldn't happen. Okay, so you wouldn't end up with this molecule. So if this is a real molecule, then there's a way to use that number of electrons in order to make everybody happy. Okay, so first, what do we have here? Second, what's the total number of electrons that we're working with? The third thing we do is we just make a little structure, a little skeletal structure using single bonds between everything. And here's our rule, okay? If carbon is present, which in this case carbon is present, there's a carbon, okay? If carbon is present, it's going to be the central atom. It's going to be the atom that you connect everything else to. Now, if there's only 2 atoms, then you just bond the 2 atoms together. It's real simple, right? But if there's more than 2 atoms, then one of those atoms have to be in the center, okay? What we're saying is carbon's going to be the one in the center if there is a carbon there, okay? If there's not a carbon there, then what we're going to do is the least electronegative atom is going to be the central atom. The least electronegative atom is going to be the central atom. So remember, page 161 of your textbook is a periodic table that gives you the electronegativity values that we use to determine what type of bonds. Remember, we subtracted the difference in electronegativity to determine if it's an ionic bond or a covalent bond, either polar or nonpolar, right? So, and I think I also gave you a copy of this in the assignment that I give you. But you can go back and you can look back and you see the electronegativity values. The lowest electronegative value, that would be the atom that would be in the center. Okay. Another quicker way to do it, pretty much does the same thing. That helps us sometimes thinking about it is just, okay, which one wants the most bond? That would be the one that would be in the center, the one that's going to do the most bonding, okay? And we'll get into that, like how do you know how many bonds one wants, I'll show you that, okay? So that's a helpful way for me to think of is, okay, how many bonds does it want? In general, how many more electrons does it want to get to 8, right? The more it wants to get, the more the bonding it's going to have to do, okay? Hydrogen is never the central atom. I don't care if it's the least electronegative. Hydrogen can't be in the center because all hydrogen can do is form one single bond. That's it. So it can't do multiple bonds, so it can't be a central atom. All right? And then we're going to start everything with single bonds, like I said, and that builds the skeletal structure. Okay? The next thing we're going to do is we're going to take and we're going to add unshared electrons to each of the nonmetals, except hydrogen. Remember, hydrogen just that one single bond, you're done. You're not adding electrons around hydrogen. Okay? So that you give everybody the 8 electrons they want. So basically, you're completing everybody's full octet. Okay? So you go around and you put your little dots, completely giving everybody the 8 that it wants. All right? So you've got your single bonds here, and then you give everybody 8 that it wants. All right? The next thing we would do is we're going to count the total number of electrons that we use to do that, and we're going to come back and look at the number that we're supposed to use that we calculated here in step 2, and we're going to see if that's the same. If it's not the same, if I use too many electrons or too few electrons, then I've got to adjust and figure out what I did wrong and how to fix it. Okay? If it is the same, then I'm good. Okay? And then the last thing that we will do is we'll check formal charge. Formal charge is actually something that's not really talked about much at all, if at all, in your textbook. But I want to go ahead and share it with you because it actually helps to kind of go ahead and know this a little bit more advanced thing in order to figure out how to do some of these things. Sometimes you can get an answer that looks right, but it's actually not right, and formal charge is the reason why. So it helps to kind of explain for the simpler problems that we do, formal charge won't matter at all, okay? But before the more complex problems, formal charge will kind of help us to adjust and fine-tune it in order to get it just right, okay? So real quick, if you got real confused with me going through this, now I'm going to do this problem for you real quick and show you what we're talking about. So step 1, determine we've got one of these, we've got 3 of these, and we've got one of these, right? The next thing we would do is determine the total number of valence electrons that we're working with. So if you have to look at your periodic table to help you with that, that's fine. Carbon is here. Remember 1, 2, 3, 4, 5, 6, 7, 8. That's you're counting your valence electrons, right? So carbon would be at 4, right? So carbon gives me 4, and then plus hydrogen's right here. So hydrogen just has 1 valence electron, so we would say 1, but there's 3 of them, so we'll say times 3, right? And then plus iodine is way over here. That's in group 17, so iodine has 7 valence electrons. So iodine only wants 1 more to get a full octet. So if I add all that up, 4 plus 1 times 3, that's 3, right? So that's 4 plus 3 is 7, plus 7 more gives me 14, right? So I've got 14 electrons to work with. Come back. All right. There we go. All right. I've got 14 to work with. Now I'm going to do my structure. I'm going to put carbon in the middle because carbon's present, and then I'm just going to put the other stuff around it. And it doesn't matter where I put what. So I'm just going to go hydrogen, 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 and I'm going to put my iodine over here. Okay? So I've got step 3 completed. I've built my little skeleton. Okay? Let me clean this up. All right? So hydrogens, remember, are set it and forget it. They've got this represents 2 electrons here. Right? So hydrogen is sharing these 2 electrons, one of them coming from the carbon, one of them coming from the hydrogen technically, but they're happy, you're done. You don't have to pay any more attention to them, okay? But step 4 says, okay, we're going to take any of these guys that doesn't have 8 and we're going to give them 8, okay? So the carbon actually has, you count my 2's here, 2, 4, 6, 8. Carbon already has 8, it's happy. Hydrogen, set it, forget it, we're done with that. But the iodine only has these 2. Okay, remember, these 2 counts for the carbon and it counts for the iodine because they are sharing those electrons, right? So this 2 counts for here and for here. So 2, and then I'll just go here. 4, 6, 8. All right, trying to make my dots big enough you can see them on the video. All right, so hydrogen's got the 2 they want. This carbon's got 8, 2, 4, 6, 8, and then now this iodine has 2, 4, 6, 8. So I've made everybody happy. The question is, step 5, did I use the right number of valence electrons to do that? So what I need to do is I need to count the number of valence electrons I used for this whole thing, and then to compare it to this number. See, is it the same? Did I use too many, too few, that kind of thing? Okay? So it's easier for me to count by 2s or 8s, right? So this, I know this one's happy. So there's 8 right there. So I'm going to say 8, 2, 4, 6, 8. So 8, and then 10, 12, 14. So I use 14 electrons to do this. According to step 2, how many electrons did I have to work with? 14. So we're good. We're happy. All right? This is perfect. All right? In terms of formal charge, we're not going to talk about that yet. We'll talk about that a little bit later on. Formal charge wouldn't have anything to do with it. It wouldn't change this problem. Okay? So we're good. That is the Lewis structure for CH3I, or iodomethane. Okay? Excellent.